We are now trying to understand orbital velocity and the time period of a satellite. In the orbit, if this is the position of the satellite and assuming the satellite is revolving around the Earth in a circular orbit, then there are two forces acting on that particular satellite. One is the gravitational force in this direction, and that it is directed towards the center of the Earth. Its value is gmm by r square, and there is an outward force acting on the satellite, which is because of the rotational motion of the satellite around the Earth, and the value is mv square by r, which is called it is called the centrifugal force. So expression for the inward force is this, and the expression for outward force is this. Now this g into me, that particular constant, is called the Kepler's constant with this much value, and the universal gravitational constant g has this value. So now under equilibrium condition, when the satellite is revolving around the Earth in a circular orbit, these two forces must be same, right? So considering this, we will try to get the expression for orbital velocity, and from that we will get the time period. So under balanced condition, when the satellite is revolving around the Earth in a circular orbit, the two forces, inward force and outward force, they must be same or equal. So m into mu by r square, that must be equal to the centrifugal force m into v square by r, and from that we can calculate the expression for velocity, and expression is mu by r whole to the power half. Now we have to find out the time period. Distance traveled by the satellite in one orbit around the planet is 2 pi r, right? We know that time is nothing but the distance traveled divided by the velocity. So time period can be written as 2 pi r divided by the velocity, and the expression for velocity is this. So by putting the expression of velocity right here, we will get the expression for time period as 2 pi r to the power 3 by 2 divided by mu to the power half. So we can see that time period is actually proportional to r to the power 3 by 2, or in other words, time period square is proportional to r cube, and that relationship is very important because this is actually one of the proof of one of the Kepler's law that we will discuss later on. Let us have some idea about the orbital velocity, time period, height, and their interrelationship. So consider Intelsat kind of satellite, which is basically a geosatellite or geostationary satellite, and its orbital height is around 36,000 kilometers, right? Now if we calculate, we can get the orbital velocity as 3.07 kilometer per second, and orbital period is almost 1 day, that is 23 hours 56 minutes and 4.1 second. Now if we consider another satellite, that is the MEO satellite, the orbital height is around 10,255 kilometer, and corresponding orbital velocity that you can calculate is 4.89 kilometer per second. Look at the orbital period. From 23 hours, it becomes 5 hours 55 minutes. So it is 5 hours 55 minutes 48 seconds, nearly 48 seconds. So as the height of the satellite or orbital radius of the satellite is decreasing, the orbital velocity is actually increasing, and the time period or period of revolution is actually decreasing. So orbital velocity is increasing and time period or orbital period is decreasing. Consider a LEO satellite which is revolving around Earth nearly with a height of 1500 kilometer above the surface. Its velocity is nearly 7.1 kilometer per second and its period is nearly 1 hour 55 minutes, nearly 2 hours, of the order of 2 hours. But if we consider another LEO satellite which is revolving around Earth at a height of say 780 kilometer, you can see its velocity is even higher. It is 7.46 kilometer per second and its time period is really less. That means within nearly just more than 1.5 hours, it actually revolves around the Earth. It completes its revolution around Earth within this much amount of time, right? So from this table, you can have some idea about the uh, velocity as well as the time period and how this velocity and time period are actually determined by the orbital height.